We're in Physical Chemistry, Chapter 18, Section 4 now. We're going to talk about the Broglie Hypothesis from 1923. Louis de Broglie was a French physicist. He said matter should behave like waves. Now let's talk about for a photon. We said before E is equal to h nu, where h is Planck's constant and nu is the frequency. Also, energy is equal to mc squared. Therefore, h nu is equal to mc squared. Now, c over lambda is equal to nu, so hc over lambda is equal to mc squared. Notice you can cancel out 1c. So we get Planck's constant over the wavelength is equal to mass times celeritis, the speed of light. Now we can solve for lambda, and we get lambda is equal to h over mc. Now h is in joules per second, so use kilograms for mass. Now matter can't go the speed of light, so he modified that equation. He said lambda is equal to h over mv, where v is velocity, lambda is in meters, velocity would be in meters per second. That's de Broglie's equation. So now we get lambda is equal to h over rho, where rho is the momentum, and rho is equal to mv. So rho is obviously linear momentum, not angular momentum. Now remember, lambda makes sense for waves, but h over rho, that makes sense for a particle. So wavelength, that's a wave property, but mass is a particle property. So this is says wave particle duality is based on on lambda equals h over mv. So this is actually a topic for the de Broglie's PhD. Now Einstein read it, but he said it was interesting. Now here's an example. Let's say that you have a mass of 1 gram. Its speed is 1.0 centimeters per second. Then the lambda would be 7 times 10 to the negative 27 centimeters, or 7 times 10 to the negative 19 angstroms. Something that tiny can't be observed. For microscopic objects, the quantum effects are unobservable because lambda is so small. Now there are two kinds of waves. One, they're traveling waves. That means if you look at the positions of the crests and the troughs, you can see they're moving. On the other hand, there are standing waves. That means if you look at the position of the crests and the troughs, they stay stationary. Now, electrons are standing waves. Now, here's an example. Here'd be like an atom, and this will be one orbital, s orbital. Here'd be like another. See the troughs, the peaks, they're all staying in one place. Now, we have 2 pi r is equal to n lambda, where r is equal to n lambda over 2 pi. So we solve for r. And then n, of course, is just a positive integer, 1, 2, 3, etc. So we get mvr is equal to nh over 2 pi. So angular momentum is also quantized. For an example, let's say we have an electron. Then the mass of the electron, 9.1 times 10 to the negative 31 kilograms. Then the speed, let's say 1.0 times 10 to the 6 meters per second. That's the speed of the electron in the first orbital. Then the lambda would be 7 times 10 to the negative 10 meters, or 7 angstroms. Now that is observable or detectable.